the types of special cores for the counter transformer, meaning everything I talked about are 3 types, so I know what to tell him next. Then I talked about its transformation in the secondary, either 1 or 5. The third thing is the types of its core or its ion core, or the 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 ion core. There is a metering type, meaning a type of core that is used with or is used when I want to use this current transformer to feed the measuring device I have, such as the ammeter, power meter, energy meter, whatever. So here it would be used to supply an analog ammeter, for example, or a digital meter, like the LED, for instance. Or when I have a CT with a transducer, meaning a current transformer, I take its current, of course, which is 1 ampere or 5 amperes, then convert them to a 24 amp signal loop that I send to the SCADA or any monitoring system I have. And if the current transformer itself doesn't have a transducer, I would have a CT transducer, in which case I get a transducer. I connect the 1 ampere to it, or connect the 2 terminals of the current here, and I output it on the other side, or dupulce, with a ratio of 24 amperes or from 0 to 10 volts, and I connect it to my SCADA system and others. But of course, in power stations, these 2 types are well known, the analog current meter or the digital current meter. In the end, you use the current meter to supply the ammeters or the power meter, energy meter, whether they are digital or analog. And I have another type, which is the protection core, where the ion core is designed for this current transformer. It is intended to supply protection devices, whether we are talking about a motor, a transformer, a generator, a bus bar, or whatever equipment I want to protect. As long as this current transformer reads the current to supply the protection device, which based on these current values will determine whether there is a problem or not, here comes the type of ion core. Don't worry, all of this is just an introduction. I will still talk about these types themselves. All right, my ion core type is protection, whether it's protection type or protection coil. I will even talk about the manufacturing, what this is made of and what that is made of, and how it operates. For example, you have a type that you find connected to, for instance, to supply its aircraft word. This is not used for protection. It does not disconnect to say, for example, that the motor is operating at a high current. Of course, this is used with motors that draw high currents. Instead of connecting it directly, I bring it to reduce these current values and then connect it to, or I connect it to mine. Whether it is, or whether it is, or whether it is. Now, this is the time we will talk about the iron core. Now, I have one of the cores we are asking about, which will be used because I will use the stick in metering. And another one will be used to power the protection devices, meaning one of them is for metering. And the other is for what? The other is for protection. Okay, very nice. The idea here is quite simple. I'm asking you a question first before I go to the core. Now you're telling me that this core, you have the iron core like this. And here you have, for example, the primary, and here you have the secondary, regardless of the type. I won't talk about window type or anything specific. I'll speak in general, okay? Very nice. Now, I'll tell you something very simple. Let's go back in memory to the notes we took in college. What did it say? It said that, okay, let's go back in memory to the notes we took in college. The idea was it would tell you that this iron core, which we used to call the iron core, is made of ferromagnetic material, ferromagnetic, manufactured from something called ferro. Ferromagnetic material means a material that is susceptible to magnetization, right? Okay, these magnetizable materials come in various types, right? There are different kinds. For example, there's silicon steel. There's something called nickel iron, and there are various types, right? It's not very important right now. I'm not going to talk about the types. I'll tell you which ones are for partitioning and which ones are for metering, because I want to explain the concept to you. The concept of ferromagnetic material is that it consists of tiny dipoles inside. What does tiny dipoles mean? It means a collection of very small magnets, which are negative, positive, or south-north, and so on, right? These magnets, which I mentioned earlier, are distributed randomly, meaning in a random manner. So the net flux or the magnetic field produced by them as a total, the final net flux is 0. This means that here, the net flux is what? It is 0. When I apply an electric current, what happens here is the magnetic field, which is the magnetic field, right? When a magnetic field passes through, what happens is that there is an arrangement or alignment of these dipoles so that they all align in parallel in the same direction as whom? In the same direction to transfer the field or mine through its passage where? Through its passage here where? In your core, exactly. So what is meant by a magnetizable material is a material that can be magnetized. This magnetizable material consists of or is a group that is randomly distributed such that its value is 0. When I apply an external magnetic field to it, these dipoles start to align in the same direction as my magnetic field in order to help the flux from the primary side to the secondary side. So they rotate with it or align with it in the same direction as the dipoles or in the same direction as my magnetic field. Here, I will play with the type so that it can be flipped or suitable for the metering core or the protection core. Okay, before I start manufacturing the material or anything like that, I want to create something suitable for metering or protection. I ask myself, what do you want in this metering? I said, I want stability, okay? And in protection, what do you want? Also, I want stability. Well, what's the difference? The difference is that in metering, I want to measure the current when. For me, the current is at a light load, meaning a light current or a moderate current, or when I have this current as a full load, or when my current is overloaded. What does a simple overload mean? It means 120% to 150% of my full load. Okay, now for the protection. Okay, now what about this? So for metering, I will measure any current, whether it's a low current, a moderate current, full load or overload. Why? Because in the end, I want to calculate the value of energy. I want to calculate the value of power. I want to make money. I want to calculate electricity bills. Right or wrong? That's the idea for metering. As for protection, here I also want to measure the currents. But does it matter to me if I read the current as light load, moderate load, or full load? No. As protection, it matters a lot to me to measure the currents, especially the currents present at the moment of what? The moment of voltage, the moment of faults. All right, so what does current at the moment of voltage condition mean? Here, the current reaches multiples, meaning several times my full load current. It reaches several times, definitely 10, 15, 20, 25, 30 times the full load current. So I will focus all my thoughts and concentration on choosing the appropriate material